So what's going to happen in 7.2 is you've been doing these, I'm going to draw in here, areas, and you should be pretty confident getting the area under the curve, right? And now what you're going to do is you're going to be revolving that area around some axis, not necessarily the x-axis or the y-axis, but either a horizontal or vertical line. You're going to take whatever that region is that you've been sketching. Maybe it was this one and you've been finding the area of it, and you're going to revolve it or whip it around and do a 360 around some axis, and what gets created is a solid. And our goal is going to be to find the volume of the solid. So what we're going to do is kind of the 3D version of what you did when you were finding area. So with area, you chopped it into a bunch of rectangles, and then you added up all those rectangles, which is the integration process. And when you were done adding up the infinite amount of rectangles that created the area, once you were adding up all these little through integration, you ended up with the area of the entire region. Well, for volume, what happens is when you whip one of these rectangular cross sections about your axis, and again, I'd still label that in dx, you'll see it creates a circle, correct? Like you can picture that whipping around. I tried to find some good graphics on here. And what happens is if you can just take and get the volume of one of these, and we call them a disk, if I could just get the volume of one of these disks and then add up the infinite amount that would be created, that's got a finite amount, but remember integration adds them all up when they're incredibly thin. If I could add up all those disks, I'd have the volume of the whole thing. So we're going to start with what's called the disk method, which will really just involve, well, what is the volume of this one red disk? It looks like a penny sitting out front. What's its shape though? Like if it were in geometry and I said, what is this? If I were to slice this red thing off and hand it to Jen, just take out some scissors and just cut that thing off. What is it? It's a cylinder. So it's really all about the volume of a cylinder. How do you get the volume of a cylinder? Do you remember that formula from geometry? Pi r squared times height. Yeah, now that you're kind of thinking about it, the height is what we've always called delta x or dx. So the height is going to be our dx in our integration. And then you said pi r squared. That's exactly what you would do because you're going to get the area of this surface right here by doing pi r squared and give it its depth with the dx, and then integration will add it all up. So if you can visualize that, it becomes quite a doable process. I want you to go into your notes. I know there's some before this. I think I'm going to start right in with the disk method, and then I'm going to go back. By the way, this process is how you get all your geometry formulas. Like, why is the volume of a sphere 4/3 pi r cubed? It comes from this process. So all these slicing mechanisms, like, did I show you guys why the area of a circle is pi r squared yet? Have I shown you that? I'm going to show you that right now so you get the historical significance. Why is the area of a circle pi r squared, and whoever came up with it? I'm going to put that right on here. You don't have to put it in your notes. If you were to take a circle, and again, I don't care how far I get, and if I were to cut it into, take out my scissors and cut like a strip off and lay it flat. Now, circle's two-dimensional, so it's going to be about area, not volume. But if I were to take that, snip it right here, and lay it flat, I'd be staring at a rectangle, wouldn't I? And if I cut all of them out like that, made them super small, and pieced them together, wouldn't I have the area of the whole circle? Right? So again, this right here, length of the rectangle is the circumference of the circle, right? Isn't it? And this right here is a tiny little piece in the radius. It's not a dx or dy, but it's a tiny little piece in the radius. So if I were able to add up all those 2 pi r drs from 0 to r, I would be able to get the formula for the area. Well, kind of take a look at this. I can bring the constant out front, right? 2 pi. What happens when I integrate x with respect to x? I get x squared over 2. What do I get when I integrate r with respect to r? r squared over 2, right? And you can see the 2's canceling. And that's why, that's one of the many, there's like 4 proofs for area of the circle, but this is the one with the integrating process in it. So pi r squared. Well, similarly, that's how you get all your volume formulas too, except you're not cutting them into 2-dimensional strips, you're cutting them into discs and washers. And we'll do the sphere if we have time today. We'll derive that formula. So what's going to happen is when you revolve something around an axis and you do it perpendicular to the axis of rotation, like your rectangle, you get what we call discs when you slice them up. You could see it. Like I'd be serving you guys each like a little communion wafer if I were to keep chopping those. And this is called the disc method, when what you slice in your cross sections, and again, I'm going to replace this with the word one slice. All right, so with the disc method, this is kind of what's going to happen. I'm going to derive it for you because it's very formulaic and I don't want you to memorize. So I want you to go here and take your black, and we're going to do all our lines and our axes in your pen or your pencil are in black. That's how we'll color code it. And then I'm going to have you draw, some function, suppose from yesterday, that went like that. Go ahead and draw that in black. And suppose you were integrating, and I'm going to call this A to B. I started at 0, but suppose you're integrating from A to B, or finding the area under the curve from A to B. That was yesterday. And what I want you to do is shade that region in yellow. So I'm going to go grab my yellow. Let's see if I can. All right, so go shade that in. That's doing it in green. I'm going to find a highlighter. There we go. All right, so shade that in. This you should be able to have found the area of from last time. What we're going to do now is we're going to revolve this around the x-axis, let's say. So draw a little revolving thing there. I'm going to take that kind of bell shape and I'm going to whip it around the x-axis. And what it's going to make is it's going to make a solid. All right, I want you to draw a representative rectangle on there, and let's do those in red, I think. All right, so go draw one of those rectangles. For finding the area, I would just add up all the rectangles, but we're going to be whipping this around, and I want you to go put a little dx on there, and we're going to whip it around the x-axis. We're going to go perpendicular like that. So my representative rectangle is perpendicular to the x-axis. I'm going to whip it around, and you got to picture what's going to be created. So dotted, take your black and go like this. We're going to go nice and slow here. A solid's going to be created, and I'm going to even make it look a little better right here. There. So can you kind of picture? It's so hard to work 3-dimensionally when we're drawing 2D, but you're going to have that solid created right there, and we're going to find the volume of it. It comes from taking a look at just one slice of this. So I'm going to slice this one off right here, right, and I'm going to remove it. And we're going to draw that one cross section. So you go like that, shade this in with your red because that's what this would be. I'm drawing this one created, that middle slice that I drew the representative rectangle for. I am going to pull that out like that. I'm going to go shade in this. And it's all shaded because I'm butting up right against the axis, so it's not a penny with a hole in it. It's a very solid disc. And then what we're going to do is take that axis, stab it through. So this will be the x-axis. Boom. That is what we call one cross section. If I can get the volume of that, integration will get me the volume of the entire solid. So you guys already kind of preempted that at the beginning of the discussion. And I have a typo here. This should say volume. So if I could just get the volume of that one disc, and I think, Owen, you said it's a cylinder, right? And we said, well, the volume of a cylinder, that's really what it's going to be, is the volume of that cylinder is equal to pi So you're always going to have a pi in front of your integral with these. Pi's in there all the time, and it's a constant because we're going to be working with these circular disks. We do pi r squared h. That's geometry. And if it were geometry class, we'd just stop and somebody would tell you the radius is 5 and the height is 2, and you plug it in and have the volume of the cylinder. Well, your radius and your height are functions of x. So your radius, let's do red again. Your radius is this length, capital R. And it is actually some function of x on this one. Whatever this was, whatever that function was, if they said f of x is x squared minus 1. For that one, that would be your radius. All right? So our height on all these is this little distance. And again, it's what we've been calling dx. So really what I've got here, if I were to take my geometry and make it a little more calculus-y, if that's a word, I'm going to have pi for sure. My radius is going to depend on what this function is up here. So I'm going to actually call it capital R of x. You can go ahead and just call it capital R if you want, but I'm going to leave that there. And my height becomes dx. But really, it's all about the cylinder. So if I want the total volume, I just need to add them all up. That's the definite integral. It's the limit as the number of those approach infinity from A to B. The constant will come out front, so you'll see in the formula that I just screenshot out of the book, there's a pi out front, but I wanted to show you why. It's pi r squared h is what it is. So I forgot the squared on there. Inside of here, I'm going to have some function that I'm going to be squaring, and then dx. So if you can integrate, you can do it. And it's all about a good picture, really. So here's the formula, and I'm going to have you write or. This is the formula when you're revolving around. I'm going to have you, let's go down here. When you're revolving around a horizontal axis, so then your representative rectangles right here are what we call dx's. But if I'm going to rotate the other way, so let's go, I'll slow down a little bit here. Suppose you're going to rotate around a vertical axis, and maybe you had this function, and you're going to go that way, then just like when we did area, it becomes not a dx, but where's your differential on this one? dy. So we're going to have that same dx dy issue. So back up to here, the formula won't change though. It's still going to make cylinders. Just instead of being standing up, they're going to be flat. We'll go draw them in a second. So it might be pi times, let's call it c to d. It might be some function of y dy. You'll know when you draw it. So next what I want to do is give you some examples for this. So where did example 1 go? Let me check. Is there one on the very bottom here? Oh, I guess we're launching right into example 2. Example 1 disappeared. So we're going to go do a problem. It says find the volume. So I'm going to circle that. That's important because you don't want to goof up area with volume. And we're going to draw in black a really good picture, because if you have a good picture, you'll be good to go. So make your axes. It says you're going to rotate about the x-axis, so I'd immediately take your x-axis and go like that. Your axis of rotation is crucial to the process. Now I'm going to go get the shaded region like we used to do when we were doing area. So I'm going to do the square root of x function. So let's go do that. Square root of x shoots out like this. And then it says I'm also bound by x equals 1. So at 1, don't make it super tiny. Let's go in there and I missed it, but you can, here, I'll make it bigger. So this right here, I'm going to revolve around the x-axis. Go shade that with your highlighter. Like that. And then I'm going to give you the process in full, because it's all about a good picture and a definitive algorithm for approaching these. The first thing you're going to do is you're going to draw your rectangle. You draw it perpendicular to the axis of rotation. What did I just say? Perpendicular. You can even see I wrote perpendicular down there. You take and you draw your rectangle perpendicular to the axis of rotation. And I would shade it in. and call that dx. All right, so I'm going to whip that around. It's going to create a three-dimensional solid. You can even kind of pretend you're doing that and then give it its little dimension right here, but it's going to create like a thimble, a solid one. It won't have any hole in it or anything. It's just going to be a very solid. Can you picture it? Can you picture it, Jordan? It's going to make that 3D shape. So what I'm going to do is down here, you're going to get used to doing this. This is what I would call a dx problem. I haven't even done a dy yet, but get used to getting that sorted in your head. My differential is along the x-axis, and this is also what I'd call a disk problem because it has no holes in it. It's solid. So this is what I would call a dx disk problem. So for me to get the volume, what I'm going to do is I'm going to do pi. They always have a pi in front, by the way, and that gets left off because you're doing pi r squared h, really. So this is really pi r squared h. And I'm going to integrate it from left to right. So on this one, I'm going from 0 to 1 are my limits. All I really need to supply is that radius. And again, I'm starting with an easy one. The radius is from here to here. And if I were to stop and put a point there, which you should, take out your green and put a point on there. If I were to put a point on here, I would call every point along that curve, and it's going to vary. That's why as I move along, these cylinders are going to get bigger and bigger and bigger, but that's okay because my function will accommodate that. But this is the point x, root x, every point. So every radius as I go along this curve is actually the square root of x. It's the function itself. So what you're going to do is replace this with the square root of x. So let's go do that. It's going to become pi times the integral from 0 to 1, square root of x quantity squared dx. And now we just integrate. What's the square root of x squared? X. So I'm going to be integrating from 0 to 1, just x dx. And now I just do antiderivatives. That's why we're doing this section right after chapter 4, so all of this is fresh in your head. The antiderivative of x is just x squared over 2. So I've got pi times x squared over 2 going from 0 to 1. So basically what I end up getting when I dump the top in is pi times 1/2 minus pi times 0. So I'm going to end up with pi halves. And what does that represent? It represents the volume of that thimble. And it would be labeled in feet cubed or centimeters cubed if I had units of measure. So the disk method is pretty straightforward. It's just pi r squared h, and you don't have to worry about anything too funky with it. But the next thing I want to do is mess with it a little bit. So we're going to change our axis of rotation. So next up, it's that exact same figure. So let's go do that. But I'm changing what I'm binding it by. So this is the square root of x. So go ahead and draw that again, square root x. But now it doesn't say bound by x equals 1. It says bound by y equals 1. So up at this horizontal line, up at 1, it kind of goes like this. And it says it's bound by x equals 0. So my boundaries are x equals 0, the curve itself, and y equals 1. Go shade that in yellow, and I'll wait for a second. So notice the region is entirely changed. It's the same function, but it's an entirely different region. Go shade it in yellow. I'm going to rotate it not about the x-axis, but it says rotate it up around. So go do this for your rotation. I'm going to rotate it up around y equals 1. So you're going to picture that thing rotating up and around. If you wanted to sketch the top half so you could get a visual, I would do that dotted. It's going to kind of be like that. It's going to look kind of like a horn. It's going to be solid, though, because, again, I'm butting right up against the axis of rotation. No air can get into that. Then here's my steps. I draw my representative rectangle. It goes from the axis to the curve. So you're going to draw your rectangle right in here. It always goes perpendicular to the axis of rotation, so go even put a little perpendicular marker in there so you've got that. So next thing I do is, this is still dx because I've got this vertical rectangle. It's still going to make a disc. It won't make a washer because there's no air that can get in there. It won't have any holes in it. Now I just need to set up my integral. First thing I need to do is figure out what my radius is. So I would write that, even get used to kind of organizing it, and then the calculus is easy. Now my radius on here, go ahead and draw it, is this. It's from the axis, and I want you to write this, axis to edge of curve. Go ahead and write that. The last one, it was the function itself, but this one it's not, because the function itself gives me this. This is x root x right here. I want that. How do you think I get the rest of this? I don't want root x. I want the distance between 1 and root x. What math operation do you do when you want the distance between two things? You subtract, correct? And we always do top minus bottom. So when I want the distance between the axis and the curve, I take the top one. The last time it was the curve and 0, so it was root x really minus 0. You could see it. But this one, it's going to be top minus bottom, whichever one's on top, the axis, and kind of get that in your head. It helps sort things out when they get difficult. Whatever one's on the top, and on this one, it's the axis, which is up at 1. Okay, so I do 1 minus the bottom, which is root x. So notice there's a little visual going on here. That little green line would be 1 minus up to root x. Now I can set up my integral. I'm going to integrate from 0 to 1 still, because I'm integrating this way. It's whipping around. Then I'm going to have r squared. And I've purposely forgot something that people always forget. What am I missing? Pi needs to be the first thing you write on your integral and the first thing you enter on your calculator when you do them calc active. It has to be. So go put a pi out front. Now it would become, am I allowed to use my calculator or do I have to do it by hand? And it's 50-50. If you are allowed to use your calculator right now, immediately go to Math 9. But don't forget to enter the pi, because that's a huge mistake, because you're so used to just going Math 9 and then entering it. Make sure you get the pi in there. If you had to do it by hand, what would you do with that chunk of stuff? You would have to FOIL it first and then use your power rule. I'm not going to do that because today's not really about the integration or the algebra, but I'm going to write FOIL, power rule, etc. You should be able to integrate that out if you had to. So the last one I'm going to do on this recording, and then we'll switch to the washers. So this one, I'm going to switch up the function on you. So let's do that in nice, neat graph here. I'm going to do y equals x cubed. So your cubic curve goes like this. And then it's also bound by y equals 8, which is a horizontal line up at 8. So 1, 2, 3, 4, 5, 6, 7, 8. And I would draw that in there. It's also bound by x equals 0. So then I would outline all of that. I've got my curve. I've got my y equals 8, and I've got my x equals 0. Go shade that in with your highlighter. And we're not doing any homework today. We're just going to get some really good notes, and then we'll practice later. All right, now it's about what am I revolving it around? What did this say to revolve it around? the y-axis. So I need to, again, I'm going to whip around the y-axis, and I always draw my rectangle perpendicular to the axis of rotation. So it's going to be whipping around this way. You can picture what it's going to make, because this is going to kind of come up here, and then you're going to have that circular top. It's going to make the thimble standing up, right? So go draw your rectangle like this, shade it in. That one rectangle will create a cylinder when it revolves around. But this is now a dy problem. So just like with area, everything is going to be about y. I'm going to integrate up the y-axis. I'm going to have a dy differential, and I need to have my function in terms of y. So when I'm looking for this radius, go draw it, because this is actually considered capital R right here. It's actually got to be a function of y this time, not x. Right now, it's x cubed, but not, that's the height. I don't want that. I want the left right. So when we had area, remember what we did for that. Instead of the function being x comma x cubed, I want to reverse that and have the x in terms of y. So what do I call the x coordinate from our area stuff? What would I call that x coordinate? Go ahead and answer me. I know I'm taping and it's awkward, but what's the x coordinate going to be? Come on. Not y cubed, no. Cubed root. Yeah, even picture this point right here. This is the point 2 comma 2 cubed. But if I reverse that and said, nope, I'm giving you the y, you'd say, oh, I got to cubed root it to get the 2. That's what we're doing. We're going in reverse. So cubed root of y. That's what this point is in terms of y. It's y cubed root y. All right, so I need the radius. The radius, again, is from the axis to the curve, axis to curve. But just like with area, we would do right minus left. So it's whichever one is on the right minus whichever one is on the left. And you can see this is just cubed root of y all along here. So that but when they get difficult, think of that right minus left. It's cubed root of y, technically minus 0, because that's the axis I'm butting up against. So now when I set up my integral, it's all about y. So here's my integral. I'm going to be integrating. I can't forget the pi, because these are going to be making discs. I'm going to integrate up the y-axis. So instead of going from 0 to 2, I'm going to go from 0 to 8. It's revolving this way, up the y-axis. I've got all these little cylinders I'm going to slice and dice, but I'm slicing like this when I'm serving it up. I'm not slicing. You can't see me on the video. Whatever. Anyway, now I need to do my radius, which is the cubed root of y, dy. And again, I purposely did something wrong that people forget. I did something different wrong on this one, but what did I forget? The squaring. Yeah, it's r squared. Then it would all be about, can I use my calculator or do I have to do it by hand? I'm going to start this one by hand just to refresh your memory. But remember, and I'm not going to finish it though, I would call this y to the 2/3 dy. How do I do the antiderivative of y to the 2/3? What do I need to do? Add 1, disguised as 3/3, right? So that would be plus 3/3 to my exponent. I'm going to have y to the 5/3 divided by 5/3 with the pi out front going, and I like to bracket it off, from 0 to 8. And I'm taking this one a little farther just to remind you, if you don't have a calculator, how do you combat 8 to the 5/3 without a calculator? Let's just take, we're almost done with this one. I might as well take it on out. So my constant in front of my antiderivative is 3 pi fifths. I would have to do 8 to the 5/3 minus 0 to the 5/3. How do you do 8 to the 5/3 without a calculator? What root is it? Fifth or third? Is it the fifth root or the third root? Third. The bottom's a root. What's the third root of 8? 2 to the fifth is 32. So that's what you do. You take the bottom and you root it. Cubed root of 8 is 2. Cubed is 32. So that would be 3 pi fifths times 32. The answer to this would be 96 pi over 5. That's what I'd call the exact answer. If you were to math 9 it, you'd get the decimal version for that. So I'm going to